Hi everyone, Mr. Hanna here. In this video we're going to be looking at some applications of anti-differentiation. And I'm just going to be doing two examples. The first one's going to be fairly easy and the second one a fair bit harder. So here we go, first question. The rate of change of the volume, V liters, of a balloon at any time, t seconds, after it is inflated beyond 6 liters is given by this. Okay, so we're talking about the volume, V, of a balloon after t seconds. And you can see from the domain here that the time is only between 0 and 3 seconds. And V to t is talking about the rate of volume change. And the rate of volume change, you can see it depends on the time, t. So here are our two questions. Express V as a function of t. And part B, what is the volume of the balloon when the time, or t, is 1 second? Okay, so first off, express V as a function of t. Well, currently we've got dv to t. So in order to get from a derivative back to the original function, we have to anti-differentiate. So we're going to anti-differentiate a function, 3t squared minus 8t plus 1. By the way, I should write a because we're doing part A. And it's in terms of t, so we need a dt there to tell us we're doing the antiderivative with respect to t. Okay, so here we go. We've got a t squared, so we need to add 1 to the 2 to make it a t cubed. And now to get a 3 here, it's just going to be 1, because 3 times the 1 gives us the 3. Next up, here we've got just a t to the power 1, so that's going to become minus t to the power 2. Now, to get that 8 there, it's going to have to be a 4, because 2 times 4 gives 8. Or you can think about like the 8 divided by 2 way. Now, plus 1, so that's just a plus t. Now, lastly, there's something I've forgotten, and that is the constant term. So I need to write a plus c for our constant term. Now, this is the really hard bit, is figuring out what c means. What is c? And to find our constant term, you always need an extra bit of information. And the extra bit of information is kind of hidden in this question. Let's read the question again. The rate of change of the volume V liters of a balloon at any time t seconds after it is inflated beyond 6 liters is given by. So what that means is at the start, so after it is inflated beyond 6 liters. So that means at the start, so when t is 0, the volume must be 6, because it says, we're talking about the time t seconds after it is inflated beyond 6 liters. So when t is 0, V is 6. In other words, V of 0 equals 6. Because of course our final answer is going to be the volume in terms of time equals something or other. So you have to answer this question, you need to be able to read the question and get that piece of information out of it. Because our answer so far is V of t. So let's write this out. We've got V of 0. So whenever there's a t, we've got 0. 0 minus 4 times 0 squared. 4 times 0 squared plus 0 plus c equals 6. Okay, so that's 0, 4 times 0 squared is another 0, plus another 0, plus c. So, equals 6. So therefore, c is equal to 6. So here's our final answer. V in terms of t is equal to t cubed minus 4t squared plus t plus 6. So it's combining our c equals 6 and this bit here for our expression of the volume. So let's read our question again just to make sure we've done it. Have we expressed V as a function of t? Here it is. Yes, we've done it. Okay, excellent. Now, part B. What is the volume of the balloon when t equals 1? So we're looking for V of 1 equals what? So let's write our equation out. Here it is down here. It's volume t cubed minus 4t squared plus t plus 6. So when t is 1, we get 1 cubed minus 4 times 1 squared, which is 1, plus 1 plus 6. 1 cubed is 1 minus 4 plus 1 and 6 is 7. So that's 8 minus 4 equals 4. And what are we looking for? What's the volume of the balloon when t is 1 second? So we're talking volume, so that's in litres. There we go, and we are done. So there's example 1 for you. Okay, so here's example 2. Let's take a look at it. So this is one that involves kinematics, so motion things. So let's have a look. The velocity of a model train starting from 1 meter to the right of the origin is given by this. V of t is 6, take away 2t, where t is in seconds, v is in meters per second, for t in 0 to 5. Okay, so let's write down some of the key things. So the first key thing, this equation, velocity with respect to time, is 6 minus 2t, and t is within 0 to 5 seconds. Okay, there's one other key thing, which is talking about the model train starts from 1 meter to the right of the origin. So if we think about this, 1 meter to the right is here at 1. And it says it starts from there. So in other words, when t is equal to 0, okay, so that means it starts, the displacement is equal to 1. There it is at 1. Or another way of writing that same piece of information, let me write it over here, is x of 0 is 1. So there we go, so there's that extra piece of information there. Alright, so let's start with part A. When does it stop? When does this train stop? Well, we need to understand that stopping means that the velocity is 0. Okay, because otherwise it'll be moving if the velocity is not 0. So we're looking for the case when the velocity is 0, and in particular we want to know what is that time when that happens. So let's write down our equation, v of t, which we already know, it's over here, 6 minus 2t, and that has to equal 0. So v must be 0. So let's find out what t must be. Take away 6 from both sides, minus 6, divide both sides by minus 2, gives us t equal to 3 seconds. There we go, done. When does it stop? It stops after 3 seconds. Part B. What is its displacement at any time t? Okay, so here's a few things that we need to know that you already know from our work in differentiation. We know that we have displacement, we have velocity, and we have acceleration. Okay, and these three things you differentiate to go this way. So to go that way, we differentiate. Let's just write this, dy dx. Or to go the other way, we integrate to go backwards. Okay, so to go from displacement to velocity, differentiate, but to go from velocity to displacement, we anti-differentiate. So we know the velocity, but we need to know displacement, so we need to anti-differentiate here. So we need to anti-differentiate 6 minus 2t dt. So that will give us 6, so that's just a 6t. Here we've got a t to the 1, so it'll become minus t to the 2. And to get 2 from that, it's just a 1. So we're done. Well, not quite. We need to add in our constant term. Now, to figure out what our... Now, remember, this is, of course, our displacement now. There you go. So to figure out our constant term, we need to use our extra piece of information. That's why it was so important that we found that extra piece of information out. So when time is 0, our displacement is 1. So let's write that in. Time is 0. 6 times 0 is 0. Minus 0 squared is 0. Plus c equals 1. So c equals 1. Therefore our displacement is given by 6t minus t squared plus 1. And let's read the question again. What is the displacement at any time t? Yep, there it is. We've got it. Okay, so now we can move on to part C. Part C. How far is this model train from its starting point? How far is it from the starting point when t equals 5? Alright, well, let's figure that out. So we want to know the displacement when time is 5. So, let's go. It's going to be the same equation as before. 6, but time is 5. Minus 5 squared plus 1. 6 5's 30. 5 squared, 25, plus 1. So you take 25 is 5, plus 1, 6. Now, here is one trick, however. So it's, after 5 seconds, it is 6 meters from the origin. 6 meters from the origin. So up on our tiny little graph, here it is at 6. Let me do a nice larger graph over here. Okay, so let's make this the displacement here. So here it is at 1 after time 0, and here it is at 6 after time 5. So let's read the question carefully. How far is it from the starting point when time equals 5? Well, it's 6 meters from the origin, but it didn't start at the origin. It started over here. So the distance that it is, so we have to write, hence it is 5 meters from where it started. It's 5 meters away from where it started. Okay. Next up, we have part D. Where is the train when it stops? Okay, interesting. Where is it when it stops? Well, we know what stopping means. It means that the velocity... means that the velocity is 0. And hang on, we remember from before that we've already talked about where it stops from part A. It stops when t equals 3 seconds. So it stops at t equals 3 seconds. And our question's asking, where is the train when it stops? So that is talking about displacement and at time 3. Okay, so there we go. Displacement at time 3. So plug 3 into our equation. 6 minus 3 squared plus 1. So remember, here's our displacement equation down there. That's where I'm getting it from. 6 3's 18. 3 squared 9 plus 1 equals 10 meters. So there we go. So where is the train when it stops? It is 10 meters. And to be super diligent, we should say the train stops 10 meters to the right of the origin. There we go, stops 10 meters from the right of the origin. Cool. Last question. How far does it travel in the first 5 seconds? Okay, this is an interesting question because it's not talking about displacement anymore, it's talking about distance. So, how far does it travel? Well, here you can see that it starts here at 1, and it does some stuff, and after 5 seconds it's here at 6. So it looks like maybe our answer would be 5, but it's actually not, because it travels further than that and then comes back. So let's actually plot a graph of our displacement. So let's put that here, our displacement versus time. So here is our equation, 6t minus t squared plus 1. Okay, so let's put that into our CAS calculator. 6t minus t squared plus 1. So let's call it something. Let's call it x of t equals 6t minus t squared plus 1. Done. So let's just check it. X of 5 should be 6. Yes, it is. Okay, so now let's plot that and take a look at it. Graphs. Where are you? Ooh. Okay, probably should, let's pause that. Okay, so you probably can't have X as the thing that we've called it. I think that was a bit of a mistake. So, let me just go into a graphs page again. Okay, we're good. Let's go to fresh graphs page. Alright, so let's try just writing that again. 6x minus x squared plus 1. Whoa. Okay, so there we go. It's a upside down parabola, so we can sketch that in too. Something like this. I think that's a pretty bad drawing, actually. Yes, it's a very bad drawing. So here you can see at time 0 it equals 1. And then at t equals 5, 1, 2, 3, 4, 5. Here, this point here, if we go up there, that is its stopping point. So you can see there's only one turning point here, which is t equals 3, as expected. That's when it stops, and it reaches a height of 10. So, in other words, where am I? Alright, so let me just draw this again. Okay, that's a little bit better. So here, cuts through at 1, and here after 5 seconds, it ends up, let's say, over here, and that is 6 meters away from the origin. And we know that at 3, when it's stationary, that's at 10. So you can see that first it moves from 1 to 10. So that's moved so far 9 meters has been traveled. Then once it's at 10, it comes back down to 6. So that's another 4 meters there. So overall, it's traveled 13 meters in its whole journey. That's the whole distance it has traveled. And you can see that there's a big difference between that and the overall displacement between 1 and 6. There's only 5 meters there. but overall it's travelled 13 metres. So that is the final answer to part E. How far has it travelled in those 5 seconds? It has travelled 13 metres. So there we go, there's 2 examples for you, so use those to help you out through the applications of anti-differentiation. See you next time.